For the last few days, we have been looking at the nucleus of the atom, looking at radioactivity, some of the things that are involved with those protons and neutrons. But now we want to focus on the electron cloud. The electron cloud, after all, is what's responsible for all of the chemical bonding. Any chemical reactions that occur because these last electrons in those atoms in the outside edge of that electron cloud are interacting. We are going to look at it in terms of the quantum mechanical model of the atom. This is a model that was developed by a man by the name of Erwin Schrödinger. He developed this mathematical equation that describes the location and energy of the electron in a hydrogen atom, and we use that information to describe other atoms as well. Schrödinger's equation has a very calculus-based equation. We are not going to get that deeply into the study of quantum mechanics. We're going to just skirt along the surface of it, and we're going to really simplify a lot of it at this level. But it has lots of implications for, like I said, chemical bonding that we're going to cover in the future. So unlike Bohr's model, which is these nice perfect rings around the atom, like planets orbiting around the sun, this particular model deals with probabilities of finding an electron in a certain location. Now, the Heisenberg uncertainty principle states that it's impossible to know both the location and the velocity of an electron. And you could say the same thing about a baseball. Knowing exactly where that baseball is and being able to calculate the speed of that baseball at the same time is impossible. What this leads us to with this idea of probabilities of electron location looks more like an electron cloud, as you can see in this picture. Now, by convention, you see that there is a ring drawn around that atom at the 90% probability line. So 90% of the time, the electron's going to fall inside that line. Occasionally, with a cloud, if you were going to draw a cloud, at some point you would have to decide where the boundary of that cloud was. Where's the cloud start? Where does it stop? And wisps of cloud could occur outside that line, just like with this atom. But that line has to be drawn at some point, and we have to make that decision. Again, we choose the 90% probability line. The electrons, as you can see, are more likely to be found close to the nucleus on this center of the atom. And then as you move further and further away from that center of the atom, the electrons are less and less likely to be found. Within this cloud, there are various energy levels. These energy levels are regions where electrons are most likely to exist. We can describe these energy levels using 4 quantum numbers, and we'll talk more about these quantum numbers in a later lesson, but they give us an address for the electron. They gradually pinpoint where that electron is located. Now, these energy levels, you can think of them as being the layers in, for instance, a jawbreaker. And if you were to cut that jawbreaker in half, you would see these layers of colors. And that's kind of similar to what the energy levels are, not of course the color, but the fact that they're spherical, they're 3-dimensional. They're not the perfect little 2-dimensional rings that we see drawn so many times. Now, the first piece of information that we need about the atom is which energy level it's located in. And the principal quantum number gives us this. The principal quantum number gives us the number of energy levels in the atom, corresponds to the period the atom is in the periodic table. If you look at the periodic table, we can figure out very easily how many energy levels copper, silver, and radium have. As we look at the periodic table, we can see that copper here is located in period 4. That tells us that copper has 4 energy levels of electrons, and that its outside energy level is located in that, or its outside electron is located in that energy level. Silver is in period 5, so it has 5 energy levels. And radium, down here at the bottom, is located in period 7 and therefore has 7 energy levels of electrons in that atom. So we can fill those values in: 4 for copper, 5 for silver, 7 for radium. And if we were going to draw a model of copper, we'd simply draw a nucleus. We would put 1 energy level, 2 energy levels, 3 energy levels, 4 energy levels around it. Now those energy levels can be thought of kind of like individual buildings that can be divided into floors. If you can imagine, this first energy level and the second, third, and fourth get progressively bigger. We can divide those energy levels into sublevels, and the higher the energy level is, the more sublevels it can be divided into. We can divide the first energy level, which is the simplest and smallest, simply only has 1 sublevel, so only 1 sublevel in that first energy level. The second energy level can have 2 sublevels. The third energy level can have 3, and I'm just drawing partial circles here for time's sake. The fourth energy level can have, as you would probably guess, 4 sublevels. Now, we draw these very simplistically as rings, but let's look at what those sublevels actually look like. These sublevels, I'm going to get rid of this, these sublevels have different shapes, as you can see here. The sublevels are named using letters. We have S sublevels, P sublevel, D sublevels, and F sublevels. And these sublevels can be divided even further, subdivided even further, into what are called orbitals. And each type of sublevel has a certain number of orbitals or orientations it can have in space. As you notice, the S orbital only has 1 orientation and therefore only 1 orbital possible. The P sublevel has 3 orientations, as you can see here, and therefore there are 3 orbitals possible. Now these orbitals are going to be the spaces where the electrons are in. The D orbitals, as you can count here, there are 1, 2, 3, 4, and 5 different orientations that we can have a D sublevel. And those orientations, again, are termed orbitals. And finally, the F type of sublevels can have 7 different orientations. So an F sublevel can be subdivided into 7 orbitals. Now, if you notice these shapes, most of the shapes have different numbers of lobes. In this F sublevel, notice we have an odd F sublevel out here that looks kind of like 2 balloons tied together, and they've got kind of like kids' floaties around the center, 2 of them, so it can like support it in the water or something, but that's kind of the shape it has. If you look up at the D sublevels here, the D sublevel with these orbitals, they look pretty much like 4-leaf clovers in most of the cases, but again, there's this odd one right here that looks like it has a floaty around the center. The P sublevels look like they are simply 2 balloons tied together in the center, and all of these have the nucleus here at the center. So these are general shapes of these sublevels. I just wanted to show you this because I'm going to ask you to be able to draw simple 2-dimensional representations of these types of sublevels, but I'm not going to ask you to be able to draw all of them or anything. I just wanted you to see how complex these electron clouds and these orbitals really are. Now, if we go on to the next quantum number, it's called the subsidiary quantum number. This quantum number tells us, again, the shape, and we just looked at some of those shapes. I want you to know that the S shape is in a spherical shape, so I'm going to ask you, if I ask you in a worksheet or anywhere else, to draw it like a sphere. The P sublevel, you're going to draw kind of like a figure 8 and fill it in. The D sublevel looks like a 4-leaf clover. I'm not going to draw over the D, it's going to cover it up. I seriously can do better than that. Let's try it again. I'm not much of an artist, but like I said, I could do better than that first drawing. Kind of looks like a 4-leaf clover. Now, on the test, when you take the test, if you draw this representation, but also draw the other kind of strange-looking orbital that looks a little bit like a p orbital with a floaty around it, I'll give you extra credit. I'm going to mark this EC so you'll know that this structure is an extra credit structure. And F, I'm going to ask you for the F orbital to be able to draw a cube. So draw a cube. I'm just going to ask you to draw one type of F orbital, or these sublevels. And that, imagine a box with a nucleus hanging right in the center of the box. And we're going to draw a lobe. I kind of think of them like balloons, drawn to the corner of each one of, again, to each one of the corners of this cube. Some of you will draw it much better than me with shading and all kinds of fancy stuff, but that's pretty much as good as I can do. I also, again, will give you extra credit if you can draw the extra structure, one of the little bit odd structures, which again looks like a figure 8 or a p orbital, but this time with 2 floaties around it. And those are the general shapes that I expect you to know. Now, the number of subshells or sublevels in the energy levels, again, I told you that energy level 1 has 1 subshell, 2 has 2 subshells, the 3rd energy level has 3, the 4th has 4, the 5th has 5, the 6th has 6, on and on. And since the first subshell is so small, it can only have an S sublevel in it. Second energy level can have both an S and it's bigger, so it can also hold a P sublevel. The 3rd energy level can hold S, P, and D. The 4th energy level can hold S, P, D, and F. The 5th energy level, S, P, D, and F. And there's a hypothetical, I'm going to draw it in green, there's a hypothetical G sublevel out there. We've never found elements big enough to need a G sublevel, but occasionally AP tests will ask us about these hypothetical sublevels. The 6th energy level, S, P, D, F, G, and H for hypothetical sublevels. Again, we've never found elements big enough to need those. As it says down here, only the S, P, D, and F subshells will actually contain electrons. So now we have energy levels. We have those energy levels subdivided into subshells, which again we think of as rings, but they are not. As we drew those shapes earlier, the atom is beautifully, wonderfully complex, and its electron cloud is no exception. The next quantum number is the magnetic quantum number. The magnetic quantum number simply tells us how many different ways we can draw those orbitals in space for each one of those sublevels, how many different ways we can draw those sublevels. That's going to tell us how many orientations, again, or orbitals each one of those sublevels can have. And we've already seen that the S sublevel can only have 1 orbital, it's spherical. The P sublevel with those figure 8 diagrams can have 1 on the X, 1 on the Y, and 1 on the Z axis, 3 orbitals or orientations. The D sublevel has 5 orbitals or orientations, and the F sublevel has 7 orbitals or orientations. Finally, these orbitals, For the final spin quantum number, these orbitals hold 2 electrons each. That is it. And those 2 electrons don't like each other. They're both negatively charged. The only way they can coexist in the orbital without destroying each other is if they spin in opposite directions. So, what do I expect you to know out of everything I've talked about today? And it's, again, right now you're going, oh my goodness, probably, what does all of this mean? What do I need you to know? First of all, for the sublevel types, I want you to know how many orbitals they have, how many orientations. Remind yourself in the picture that the only way you can draw a sphere, there's only one way. The P can be drawn 3 different ways, so there are 3 orbitals possible in a P sublevel. The D can be drawn 5 different ways in 5 different orientations, therefore there are 5 orbitals. The F has 7. And since each of these orbitals can hold 2 electrons, the total number of electrons for an S sublevel is 2, for a P, 6, for a D, 10, and for an F, 14. Then as far as the energy levels are concerned, how many sublevels are there? We've already established that the number of the energy level tells us the number of sublevels it can be broken down into. Energy level 1 can be broken into 1 sublevel, energy level 2 into 2, energy level 3 into 3, energy level 4 into 4, etc. The names of these sublevels: only an S in that first energy level, an S and a P in the second energy level, but it's very important for us to know which S and which P we're talking about. So in the first energy level, we call this a 1s, and it's very important to know whether the electron's in the 1s or the 2s sublevel. So if it's on the second energy level, we put a 2 in front of it to indicate that. In the third energy level, we can hold an S, a P, and a D sublevel. We put 3s in front of those to show that they're in the third energy level. And finally, in the fourth energy level, we can have S, P, D, and F, and we indicate those by putting 4s in front of them for the fourth energy level. So 4S, 4P, 4D, and 4F. Since these orbitals can hold a certain number of electrons, or these sublevels can hold a certain number of electrons, a 1s can hold 2. Please don't make the mistake of trying to multiply by the numbers in front of those sublevel letters. It doesn't matter if it's a 1s or a 7s, it still holds 2 electrons. It doesn't matter if it's a 2p, a 4p, a 6p, still holds 6 electrons, as we saw in the table above. D's hold 10, F's hold 14. What that means is that the first energy level can hold a total of 2 electrons. If we add up the 2 and the 6, we see that the second energy level can hold 8 electrons. The third energy level, 2 plus 6 plus 10, we get 18 electrons. And finally, for the fourth energy level, 2, 6, 10, and 14 added together gives us 32 electrons. Now, we could go to higher energy levels, but I just wanted to show you an example. Now, very quickly, before we conclude this lecture, let's look back at the periodic table, and let's notice something. Notice that we have a section here that is 2 columns wide. A section here that is 6 columns wide. A section here, these transition metals in the center, 10 columns wide. And down here at the bottom, when we're looking at our inner transition metals, we count across and we see that this is 14 columns wide. 2, 6, 10, and 14. This should be familiar from our table up here. 2, 6, 10, and 14. Coincidence? I think not, but we'll talk about that in the next session.